At this point, I think we mainly concluded what I'm going to say about distance protection. It's not everything, but I hope enough that I can fit into a small training like that. And I would like to move on to another subject which is very interesting and closely related to the distance protection, the so-called, or not the power swing blocking, not so-called, but the power swing blocking. The power swing blocking is something where we again look at the system and we're going to use a model, and the model we're going to use is a so-called two-machine model. In this case, a lossless two-machine model where we have a generation on the one side and a motor or load on the other side. And in between, obviously on the generation side, you have a generation impedance, source impedance. Then you have the XL, the line impedance. So our relay would typically be at the VA, that would be the one bus bar on the left. VB is the bus bar on the right, not the A phase, B phase, sorry. So left-hand bus, right-hand bus, VA, VB. And then the load side impedance, okay, the load impedance on that side. One can typically also consider this to be two sections of a transmission network, the generation side close to the generation and the VM close to the load side of a transmission network. And you can reduce it. A complex network can be reduced to this two-machine model. It's not that we would apply a system with one generator and one motor. The complete power system can be reduced. You can reduce your sources, your generations to one big generation equivalent. And this is very common. If you look at a relay, if you place a relay at the bus A over here, and then that relay with its current voltage measurement will look forward towards the XL, and whatever that relay would see would be defined, a short circuit in front of it would be defined by the source impedance. That source impedance is all the generation behind it. And that would be the VG and XG. That's our one equivalent source. You can reduce the entire source of that one relay to one equivalent generation. And the same in front of it, you can have the ZL and the remote bus bar one equivalent load. So the two-machine model is very, very effective in analyzing and modeling the power system. From that equation, you can derive, from that diagram, that model, you can derive this equation here. And I'll show that in a graphic form, but just to show you what we have here is P power, so the power transferred from the generation to the motor, the active power is equal to the VG times VM, so the voltage at the generator side and the voltage at the motor side divided by the sum of those impedances in between it. And because we're using this lossless model, we can have a very simple sign of the angle between them. So let's have a look at the definition of that. That's shown in this diagram over here. What is missing in the diagram is obviously the load current, but that is shown at the top here. You can see the load drops, the three load drops. The load current would effectively be exactly at the bisection angle, vertical at the bottom from the source upwards. That's the load current. Remember, the load current for active power, for P, we get real power is only if the current is in phase with the voltage. Okay, so in this case, it would be exactly in the middle. And the current would flow left to right. There's only one current in this system. There's no other shunts. It's flowing from the generator to the motor. That's the current. And this is the current shown here. And because that current is vertical, in these reactances, it causes a voltage drop, which is 90 degrees. Current is 90 degrees in reactance going to be leading the voltage. That's right. Lagging. The current will be lagging the voltage, sorry. Lagging the voltage, that's why I see, sorry about that. The angle here, it's at 90 degrees to the current that we should not show the vertical current. And that then increases the angle at the bottom. So you can see if the load current were to increase, you can see the angle is going to increase, and if the load current decreases, it would decrease. If the current was zero, there would be no voltage drop, and the generator and the motor would have exactly the same voltage. That is a little bit. And as a power swing indicates, obviously if the power is increasing, the angle goes up and down between the generator and the motor. And this top diagram, one can show that in a little plane like this, the relationship of that angle, with the angle between the source and the generation here, from 0 to 180 degrees, a simple sine wave. And the magnitude of the sine wave is the P max. The Pmax would occur at when the max sine is equal to 1 at 90 degrees. So at 90 degrees, so when this angle between the source and generation is 90 degrees, we have the maximum current. At that point, no, the current could get larger, but the power does not get larger. Why does the power not get larger? Because if the angle gets larger, we go, as we'll see on the next diagram, into an area where the voltage starts decreasing very rapidly, and then the power gets smaller, because power is current times voltage. So simply increasing the current is not going to just keep increasing the power. At some point the voltage is going down, and then the power will go down again. So that diagram, now let's look here and we define some points. The first thing we have to identify is that in a normal steady state operating condition, the PM and the PG are the same, because our problem is the network does not store any energy. Okay, so what power is coming in on the generator side into the electrical system must go out on the motor side. The electrical system, as we have defined it there, has no means to store power. Okay, unfortunately not, I think. So that would be a typical operating point, and we have drawn that here. Then you can see now the current is shown here. I showed it vertically in the middle. The current is there in this model, and the generator is over there, the motor is over here, and the voltage drop from the generator side and the line impedance and the motor side is shown like that. The VA would be now our relay location. So at our relay location, we have pure a power factor equal 1. Current and voltage are in phase. Okay, obviously there will be power factors will be different here and there, because there the current and the voltage are not in phase. But here we have exactly power factor 1, current and voltage in phase. It's in our model. 60 degrees, and you can see the 60 degrees is very close to what we call Pmax. Why do we have a Pmax? That Pmax is what is referred to as a theoretical steady state limit. Power, so load angle limit, 90 degrees is that. Why is that so? Because if you imagine that the load and the generation want to transmit more and more power, you can see the angle will shift towards 90 degrees. And when you're at 90 degrees, the current will have increased. Okay, but if you now want to put even 1 watt more power through the system, you will try and increase the current. What will happen? The angle will increase, but you can see the power will go down. And the power that can be transferred, this is an important thing, this is the power that can be transferred. Surely the generator can maybe generate more power, but the electrical system, it cannot transfer that power, so the motor does not receive that power. And then you have a problem, because then there is power, real energy, at the generator side, which does not reach the motor side, because it cannot be transferred. That means the generator needs to store that energy. Generators can store energy a little bit. Sounds interesting. How do they do that? They increase their rotational speed. They store it as rotational energy. The generator will accelerate, and we have then a problem. The frequency will go up, and we get then already a power swing condition. So the theoretical steady state limit is Pmax. Obviously it is theoretical because we cannot operate there, because there's no tolerance. The system will always have some jitter, and if you're sitting at the maximum, the smallest jitter, and you're going to slide down the other side. That's why a practical limit here shown 60 degrees. 60 degrees is a very, very high limit. Typically you would be operating at Pmaxes around about maybe 40 degrees. 60 degrees is a fairly extreme value already. What is 120 degrees? 120 degrees in this case, if 60 degrees was our operating point prior to a system disturbance, then 120 degrees corresponds to the transient stability limit. Remember, the 90 degrees was a steady state stability limit. 120 degrees would now be referred to as a transient stability limit. Why? It is quite simple. Remember, our generator was generating PG and our motor was consuming PM. And as long as we are on the left-hand side of that 120 degrees, the system can transfer PM and PG. If we go beyond 120 degrees, the system can no longer transfer PM and PG. That means we have passed a transient stability limit. So in a transient method, if something happens, there's a disruption, a fault, then you can move from the 60 degrees, you can move up, But if you move beyond 120 degrees, you've passed the transient stability limit and the system will go out of step. These values are quite interesting for when you apply the out of step protection, which we'll refer to later on a little bit. But for the power swing blocking, it is interesting to know, but it is not of any significance in terms of settings or anything like that. It's just parameters one should know about. Another point you then get to, interesting, is 180 degrees down here. It's so-called out of step point. That's where the systems have turned completely open. It's very interesting in terms of our distance protection. You can see here what happens at our relay A, the voltage is now 0. What will the impedance be? The impedance will also be 0. Remember, impedance is V voltage divided by current. No matter what the current is, the current will not be 0. You can see the current is really large, the load current. During the point, the load current has increased a lot because we need a big drop between the left and right side, but the power transferred is 0 at the relay location because power is I times V times cosine phi, and cosine of 90 is 0. There's no real power being transferred, only reactive power, VARs. No watts, only VARs at the relay. But the impedance is 0, which is a problem. Okay, these diagrams are very interesting, but remember we are looking at the distance protection, and the distance protection we're used to seeing impedances. These are voltages, okay, remember it's real voltage. Okay, current was also shown, but the voltage, and these I times Z are also voltages. We are looking, and to transfer these voltages into the impedance plane, you simply divide all the IX voltage drops here by the current, and then you get reactance. Okay, so try and take this diagram that we have here now, and I'm going to transfer it over here into the impedance plane. Now we have the impedance plane R and X, and we draw a circle because the trajectory of the power swing as we move from that 0 degrees, you see right at the top 0 degrees, to later on we'll see the 180 degrees will be at the origin. That trajectory you move on in the impedance plane is a circle. It's a bit, just for clarity here, obviously in a theoretical point of view, was that lossless model. Remember we had a lossless model which was just X, and at 0 degrees the current was equal to 0, so the impedance would be infinite. Okay, now I can't draw infinite in a circle or any plane, it's somewhere off the range. So that theoretical case we actually had there would be the special case of a circle where the circle has an infinite radius, a straight line. Okay, and that point 0 would be infinity somewhere on the left or right hand side, depending on which, if we're on the generator or motor side. But in the practical sense, we will not have a perfect lossless system, so the power swing or the trajectory will be a circle. And the position of the circle, interesting enough, also depends on whether the voltage on the generator side is a little bit bigger physically than on the motor side. That can also be, the circle can be below or on top, but at the end of the day, it'll be a circular characteristic, the trajectory of the impedance during a power swing. So let's look at some points. 0 degrees will be far outside, and the measurement there will be not really possible because it's at current effectively 0. We're not measuring any effective current, so an impedance measurement there is very theoretical. But once we leave the point 0, we get to a very real impedance we can then measure because the current then is no longer 0. So this is unfortunately a little bit of a theoretical point, this angle 0. Also, when you see it later on doing tests, will not be practical. And you can see the big distance between that theoretical point 0 and 60 degrees. It's very interesting. If you see a circle, typically, if you're going to divide a circle up into angles, you think 0 degrees, somewhere here 90 degrees, 180 degrees, and so on. Not the power swing circle. The power swing circle, unfortunately, 0 degrees, and you can see the 60 degrees is down here. It's what we understand. If you think of a distance relay, the distance relay is sitting there at the origin of this diagram. And what would you have under a typical load? If you have a typical load export, you see the load somewhere here. Okay, maybe depending on the power factor in that range. You see it in the RX range somewhere here. That's where you would see your load impedance. So this is really quite understandable for us now. A normal load condition, or not normal, very high load condition already. Remember I said 40 degrees would be normal load. 60 is a very, very high load condition. Would probably not, if we set our relay correctly, will be either in the load cutout, but not in the reach of our distance setting. So our distance setting should not encroach into that. That's what we apply. We apply load encroachment, other factors to prevent the distance relay from seeing this inside its characteristic. Remember the next point was the 90 degrees, not so interesting, but the 120, our transient stability limit. So a power swing, in theory, if there was a disruption in the system, the impedance could move from that 60 all the way up to 120, and now you can see that could be inside. So between that 60 and 120, we could be inside the distance relay reach, and we don't want the distance relay tripping because it's not a fault, it's a power swing condition, and we need to apply the power swing blocking for that. Okay, and obviously if the swing continues to 180 degrees, in theory it could be at 0 ohms, okay? This circle does not have to go through the origin, okay? Just to mention, in this case it goes through the origin because our relay that's measuring this is sitting at the so-called electrical center. So it's sitting exactly halfway between the generator and the motor. If we are sitting a little bit to the left or right of that point, the circle will cross either above or below. So it'll be a circle crossing not exactly, but that doesn't matter. The trajectory will come into the impedance settings here, not necessarily going exactly through the origin, but this is one example, just to understand. All right, for this setting, now we're going to come to the power swing blocking settings in the relay. It says there are no settings required. Obviously, you need to set what you want to block, but you don't have any settings that you have to set the frequency or the blinders, or there's no complicated settings needed because the power swing blocking function works autonomously. It is very effective, can detect swing frequencies of up to 10 hertz. So it means that you have 10 rotations per second, which is normal power swings will be in the range of about 2 hertz, up to 2 hertz in a normal power system. But if you leave it there, eventually it can accelerate up to that speed, but that would be very, very unusual. So the maximum power swing frequency is not an issue. You can detect the power swing during single pole open conditions. We'll show that in the diagram later on. Okay. If the power swing changes to a fault, it'll unblock. We'll look at these conditions later on. So this is just some features of the power swing blocking. Out-of-step protection in CPROTEC 5 is a separate function, okay, that you would use. If you want to use out-of-step protection, it's the same principle behind it, but it's a different thing. It's not distance protection. It's a function that you apply to recover, like a say disaster, one can call it. If the system has a real serious disaster in a system where it's like cascading tripping, then you need to island the system. It's a separate concept, not a distance protection concept, and therefore it's a separate function, the out-of-step protection function in the CPROTEC 5 relays. So how does it work in principle? Just quickly, we need to move a little bit. The power swing detection will apply around your set zones. You see the yellow would be your distance set zones, your largest set zone. Automatically, no settings required. It will automatically in the background apply a boundary around that, and then it will monitor the impedance on a continuous basis. And each of these red dots is measured impedance is separated by about 5 milliseconds. So you can see it does a measurement, then every 5 milliseconds another one, and measures the impedance and then checks the trajectory continuously of that. And that's done all the time, even if the impedance is far outside the pickup characteristic. All right, that block, then you can see there as it moves into the characteristic now, it needs to, if it moves there, then your distance relay would start picking up and trip, and so we have to have the blocking active by the time it reaches the set zones. And the techniques for the blocking use a lot of criteria, and only a few have been extracted here for the explanation. I don't want to go into all of that. It is really, really very intricate function in terms of the detection. But to summarize quickly, we have here a monotony criteria. That means it must keep moving in a defined direction. You can see here we have the delta x's decreasing and the delta r decreasing. You can have a change of the x, but the r was still decreasing. This would still be a power swing. It is a fairly monotonous movement because only the x change direction, not x and r. That would be a normal smooth trajectory, as one would refer to that. On the other hand, if you get an abrupt reversal like that, that is not what a power swing would do. A power swing would not do an abrupt reversal like that. That would be a criteria to reset the power swing blocking as one of the criteria, not the criteria. It's a number of criteria working in parallel. The continuity criteria is rather interesting, because if you have a power swing, obviously you can have a stationary load somewhere, but that's not inside the relay where it enters the relay. Once you have a power swing and the thing starts moving, it has to keep moving. If it should all of a sudden decide to stop like this, then it is no longer a power swing. Because remember, if it's inside the relay characteristic, this is somewhere at 120 or 150 degrees on our circle, remember, that is not a point where the impedance can stop. It can stop at 60 degrees or 40 degrees, that's somewhere out here, but not in there. It cannot stop. If it stops there, it's a fault, typically a three-phase fault. Very, very unlikely to happen, but some people like to test things like that, and the relay will detect that and reset the power swing blocking if that happens. The smoothness criteria is a very commonly one that's used to check, because that's also a very interesting one. The distance between each of these measurements, remember, every 5 milliseconds you measure impedance, the distance is going to be fairly constant, because the rate of movement is quite constant. And it's also interesting, I didn't mention that earlier, if you remember that circle we had before with the 0 degrees at the top, 180 at the bottom, the movement when you're close to 0 is fast. When you come to the bottom, the movement slows down. Okay, so where it is interesting for the relay, the power swing impedance trajectory movement is fairly constant, fairly slow, but it must be continuous. It cannot jump. It cannot be slow and then have all of a sudden a rapid jump like that. That is not possible. That would be a reset. The jump of the trajectory would be a reset criteria for power swing blocking. This is just an interesting diagram just to show. Remember, we had a circle all the time some years ago. Some student in the development department made a model with 3 machines, not 2 machines. And you can see if you have 3 machines swinging, they can swing at different, they interfere with each other. So 3 machines interfering, and then you get a slightly, but you see the movement here is smooth. There is no jump in there. It is like moving along a fairly complex path as such, the 3 machines swinging, but there are no jumps. This is just a continuous power swing. No fault or anything, it's just a power swing. And the advantage is obviously the other older or historic way of measuring power swings was using blinders, and it was just to show that with the blinder technique it's difficult. But the blinder technique sees when you cross the one blinder and it starts a timer, how long till you reach the other blinder. And you can see there will be some difficulty here, but you sometimes cross the one and you don't even reach the other one, go back out. And so the blinder technique will not work, whereas the power swing detection as we have implemented in Cyprotec 5 works quite well. It's the same power swing detection as it was also used in Cyprotec 4. Now some diagrams just for interest. This is a power swing, and you can see the power swing blocking at the bottom is picked up. Unfortunately, I must apologize, this is done with Cyprotec 4, but as I said, the technique is still the same. It's around about a 2 Hertz swing oscillation we see here, and you can see the typical characteristic of a swing. As the current increases, the voltage down here decreases, and you can see around the left there, the power swing is there, and at the bottom of power swing detection is picking up and blocking. And then over there you get also the pickup by the relay as it swings in. You can see where the current reaches its peak, the voltages go down, the relay actually picks up, but no trip because the power swing blocking prevented the tripping. Then over here, in the middle of the power swing, you get a fault condition. You can see the fault is here on the C phase. The C phase current is now a fault current. The fault current magnitude is smaller than the power swing current. Over here, the voltage just stops. Obviously, the voltage does not continue with its trajectory, stops. And you can see the pickup of the C phase zone 1. Okay. In this model, the tripping was not done to the break. Otherwise, the current would have stopped. It would have a single pole dead time here, but it was just, unfortunately, the model used at that time did not really trip the breaker. It was to show the zone 1 trip would have come. And the other phases, the power swing blocking stays on over here. That is clear. It's one example. That's another example here. Here, the relay now does trip in the A phase, and you can see the dead time. You get the power swing continues in the remaining 2 phases. And here it's a more accurate simulation. You can see the power swing frequency is not constant. It starts off with, you see the swing frequency you can calculate from the dip here to the dip over there and the next dip over here. The time interval there, that's one rotation. That's from basically here, 0 degrees back to 0 degrees. That's one times around the circle. And you take the time difference there, I can't read that exactly now, that would be related to the frequency. I think it's around from 2.5 seconds to just under 3 seconds, so it's just under half a second. So it's round about going to be a 2 to 3 hertz swing. But you see, as we move on, the interval gets shorter and shorter, the swing frequency is increasing. So at that point, we have around about a 2.5 hertz swing, and then right at the back, we have an interval of about only 250 milliseconds, around about 4 hertz at the end. So the swing frequency changed there. But it doesn't matter. At the bottom, you can see the power swing in the pole, open pole is obviously reset, but in the two connected poles B and C, the power swing blocking is active and prevents tripping during the one pole dead time. That's the fault inception. The power swing blocking resets, and that's the reclosure. And see, after the reclosure, the power swing continues, and the power swing blocking becomes active again, and there's no tripping of the relay due to the power swing blocking. That's just a note. Okay, in CPREC 5, you will not see that gap that is shown here. In CPREC 4, you did see this. So if you see this gap here, that is not relevant. The power swing blocking is still active there, and that's why in CPREC 5, you will not see a gap there. But in CPREC 4, there was a 80 millisecond timer, which when the measurement drops, what you see is the measurement drops off due to the jump, but there's a delay on reset of the function of 80 milliseconds, which bridges that drop off there in CPREC 4. In CPREC 5, we changed the signal output. The signal output includes the stability timer, so you don't see the gap on CPREC 5. The functionality is the same, because you are still blocking in that gap, but you get some more consistent information you see in CPREC 5. And one of the final things I want to show here on the power swing blocking is an example. Here you have a transmission system with 2 feeders and 4 relays, D1 to D4 on the transmission system at the top. And at the bottom, you have here, this was in some South American country, I don't remember say which one, but it's I think it was 220 or 300 kV, long transmission lines, and this was a bus bar pretty much in the middle of the transmission system. This is the load side and somewhere quite remote generation there. And what happened on this bus bar, somewhere in the middle of this transmission system, there was a distribution transformer, and on the LV side of the distribution transformer was a fault, and that fault was not cleared immediately. I think it was some animal on the LV side of the transformer, and it was somehow not cleared properly or it stayed on for a certain time. So try to visualize this, and we will look at one of these relays. I can't remember which one of the 4 relays here, how it would see this fault on the LV side of the transformer. So the 3-phase fault over there, let's say on the LV side of the transformer. And what you don't want is a trip of any of those feeders. That would be a disaster if your transmission system trips due to a fault on the LV side of a transformer connected to the one bus bar. And here you can see this is the D4 relay. Okay, we can maybe go back. See, D4 was the relay over here. This relay sees obviously that fault in reverse direction is what you will see now. You see there's a load condition transferred. So D4 is actually not quite, the load would have been on the other side. Sorry about that. I think the diagram not that accurate. And I also remember, so far as I remember, the load did come in from the left-hand side, not the right-hand side, but just a symbolic diagram, this one. Then you jump to the reverse fault. Okay, and then this reverse fault stays on, and now the voltage on that bus bar, that transformer connected bus bar is dropping. And remember what happens if the voltage drops, the transmission system can no longer transfer the power, and the angle is going to increase. We're going to go into a power swing condition. So we jump onto a circle. There's our power swing circle, and that's going to circle right into the zone 1. And that means we would trip the transmission system. So the power swing blocking needs to pick up at the bottom before we reach the zone 1 and then block it. And that's what happened correctly, and there was no tripping, no incorrect tripping due to that.